Okay, good afternoon. So just an announcement for tomorrow. So I will use the tutorial tomorrow to for an example to run an example related to synchronization. So tomorrow there will be a tutorial session. So just a note. Let me just check if it is on the website. Yes, it is. So 2nd of February, there's a link on the website for the tutorial. So hopefully we get to finish synchronization this lecture. Okay, so we talked about semaphores, and we used them to implement this reoccurring example that we have been seeing, which is basically the producer-consumer problem. Now, we stopped here last time. The order of operations in producer-consumer problem matters. So in this example, in this slide that is in front of you, I have changed the order of calling P here from the previous slide. So instead of first calling empty slot.p and then calling mutex.p, I have reversed the order. So I'm calling mutex.p first and then empty slot.p second. And the question is, does this matter? And the answer is yes. Unfortunately, the order of these operations matter. And in this particular example, this could lead to deadlock. So let's say if you have one thread that comes and gets into the, let's say a producer comes in, it calls this mutex.p and then checks the empty slots and gets blocked here because there is no empty slot. Now, no other producer now can come and produce. Sorry, no other consumer can now come and consume items to make free space for the producer, because the consumers are going to check this. There are items in the list. So next they're going to call this mutex.p, but because the producer had already called p and didn't have a chance to call v, now this the mutex is 0. From 1, it has become 0, and this blocks the consumer. So producer wants the consumer to consume an item, and consumer wants the producer to release the mutex or call v on the mutex. Now there's a dependency between the two, and none of that could happen because producer is waiting on the consumer and consumer is waiting on the producer. So you have a deadlock situation here. What about the order of V's? You can actually convince yourself that that one doesn't matter. So if you reverse the order here, either these two or these two, it probably doesn't matter. I mean, it definitely doesn't matter because in this case, you're basically signaling, and it doesn't matter when you're signaling. It really matters when you want to go and wait. So in this example, the order of V's don't matter. It doesn't matter. The order of P's does matter. Okay, so we saw semaphores. Now, this is from Dijkstra's paper in 1968. So Dijkstra was the one who introduced semaphores, and he said that there's a problem with this with the semaphores, and that problem is that they're dual purpose. So as you can see here, he says that they can be used for two completely different ways, and this is precisely what we talked about. So we talked about mutual exclusion and scheduling constraints, meaning that the wait and signal. So we're using them in both ways for both mutual exclusion and to do scheduling. And as a result of this, we get to this problem that a code that uses semaphores is usually hard to reason about. When you see semaphores, their initialization is important, their order is important, and at the end of the day, you don't know which semaphore is used for what. Is this semaphore used for mutual exclusion? Is this semaphore used for scheduling constraints? And it's just hard to analyze. The solution is basically to use monitors instead of semaphores. Now, what is a monitor? A monitor is a single mutex and bunch of 0 or 1 condition variable. So we're going to use the mutex solely to create mutual exclusion, and we're going to use condition variables for scheduling constraints. So this way, we have modularity. So if we see a mutex, we know that this is for mutual exclusion. And if we see condition variables, we know that it's for waiting and for scheduling constraints, for waiting and signaling. Now, what are condition variables? So I started with monitors. Monitors consist of a mutex and a bunch of condition variables. Now let's see what condition variables are. So condition variables are basically used for the scheduling constraint, and what they do is they make threads wait for events. So the thread that wants to wait calls condition variable.wait, and then the thread that wants to send a signal calls condition variable.signal. We also have the broadcast functionality that we didn't have with semaphores. So these are the three operations that are defined on a condition variable. As I said, there's the wait function, there's a signal function, and there's a broadcast function. Let me start with the signal and broadcast. These are easier to understand. So let's say in the producer-consumer example, as we will see the code this time using condition variables, let's say the producer comes and the queue is full. So then the producer can call wait. Now, if a consumer consumes an item, it can signal waiting producers to come and produce an item, put their item. So the consumers could call signal. Or if the producer, if a consumer comes and the queue is empty, there is no item to be consumed, it can wait. So it goes to sleep, it waits. And later on, when a producer comes and produces an item, it can send a signal to the consumers to come and consume an item. Now let's talk about wait. As we can see, this wait as an input gets the mutex or a pointer to the mutex. The reason for this is when you call wait, you're going to be suspended. So a thread that calls wait will be suspended. Now, when you get suspended, if you have already locked the mutex, so if you have called mutex.lock and now going to sleep, you want to release the mutex before you go to sleep. Otherwise, if you lock the mutex and go to sleep without releasing it, then you could end up having a deadlock, right? Because let's say the producer, there is no empty item, so it has locked the mutex, it checks the queue and there is nothing in the queue. The queue is full. It's a producer and the queue is full. So now it wants to go to sleep. If it goes to sleep without releasing the lock, now no consumer can come and consume because they cannot lock the mutex because the mutex is already locked. And the one who is supposed to release it is in a sleep, waiting for me to consume. So you will get that deadlock situation again. To avoid that, internally, so if in the future in the future lectures when we talk about multi-threaded kernels and the implementation of this, so again, I'm going to tell you what is inside wait, but we're not going to go deep into implementation of it. We're just going to look at the functionality. And later on, we talk about implementation. But if you look at wait, it gets this mutex star m. So it's going to be atomically at some point call m.unlock and then go to sleep. So it will unlock the mutex and it goes to sleep. Now, at some point, another thread comes and signals, and the thread that has gone to sleep wakes up. So what do we mean by wake up? By wake up, we just mean that so this go to sleep changes the state from running to waiting. Now, if another thread comes and signals us, the state from waiting goes to ready. This doesn't mean that we're going to start running. It just means that the state will change to ready. At some point, the scheduler will pick us. We will be the one who is going to execute. Where do we wake up? We'll wake up here, the next line after go to sleep. What are we going to do? What we're going to do is, let me clean this up a little bit. So what we're going to do after we wake up, we're going to say m.lock again. The thing is, we entered wait. When we entered wait, the mutex was locked. We locked it and we entered wait. Then we unlocked it and went to sleep. Now we have waken up, so somebody signaled us. The first thing we have to do is to lock the mutex again. So m.lock will be called here. Now there is a possibility that this mutex is locked with someone else. In that case, we get blocked here. We could get blocked inside the wait. And at some point, the mutex is going to be unlocked, and then we get to lock it, and then we get out of wait. So when we get out of wait, we have the mutex locked. Now this whole thing might be a little bit confusing, so I'm going to repeat myself one more time. What is going on? So let me repeat myself one more time. You enter wait while you have locked the mutex. Inside wait, which we're not going to be concerned about, so I'm just telling you the functionality. The implementation comes next, in the future lectures. But the functionality of wait is it unlocks the mutex because you're going to you're going to pass a pointer to the mutex that you have locked. So the wait will internally release that for you. So it releases the wait, the mutex. It puts you to sleep, and we context switch to someone else. So we're done with this thread. This thread is going to go to sleep. Now, at some point in the future, this thread will wake up. Excuse me. So at some point in the future, this thread will get a signal. Its state will change from waiting to ready. And later on, the scheduler will pick this thread and starts running it. Now, where do we start running? We'll start running inside wait. Right after we went to sleep, we wake up there. What do? The first thing we're going to do inside wait is to call m.lock. And again, you're not going to do any of these, right? These are all implemented for you when you use the thread libraries. So you don't need to do this. I'm just telling you what the functionality is. So internally, wait is going to call lock on your behalf. Now, there's a possibility that this mutex is already locked, but by someone else, right? In that case, you will be blocked again for the second time. The first time was this go to sleep, right? You went to sleep. Now, if you call internally m.lock is called, there is a possibility that you go to sleep again because this mutex might be locked by someone else. So you will be suspended for the second time, probably. But then eventually, that mutex is going to be unlocked, and you're going to get up, and you're going to be able to lock it, and then you get out of wait. So you went inside wait while the mutex was locked. You get out of wait while the mutex is locked. Now, we'll see examples of this, and hopefully it makes more sense. Let's continue with this. Let's talk about properties of condition variables. What are the properties of condition variables? The first one is that they're memoryless. What do I mean by memoryless? So I'm comparing condition variables against semaphores. So let's say you initialize your semaphore to 0. So your semaphore is initialized to 0, and then you call v 10 times. So 10 threads come, all of them call v. At the end of this, you expect your semaphore to have the value of 10. Now, if 10 threads come and call p, then all of them are going to they're not going to wait because they're going to just decrement 10 to 9, 9 to 8, and all the way to 0. So none of the 10 P's are going to wait because we previously called v 10 times. This means that your semaphore has memory. It memorized how many times you called v, and now it's using that memory to let P's go. With condition variables, if you call signal 10 times, so say condition variables that signal, and then you do this 10 times. If there are no threads waiting, then your signal will be wasted. Your signal will be forgotten. We're not going to memorize this. So let's say 10 times you call signal, and then one thread comes and calls wait. That thread is going to wait. So it's not going to use the memory that, oh, 10 times before signal has been called. Now I can use one of those. No, all of them are wasted. So we're not going to memorize the signals. So that's the main difference between condition variables and semaphores. We're not going to memorize them. Now, the other thing about condition variables that you have to always adhere to is that you have to always lock the mutex and then use the condition variables functions. So wait, signal, and broadcast, you have to have locked the mutex before you call these functions. The third point is that the wait function that I described, the functionality of it, has to happen atomically, meaning that you have to release the lock, you have to unlock the mutex and go to sleep atomically. So you can't first release the lock and then before you go to sleep get interrupted. You have to release the lock and go to sleep before you get interrupted, right? Otherwise, the state would be in a undefined state. Now, how to implement this? Again, wait until we talk about the implementation of condition variables. For now, we just take it as is. So we just assume that wait does what we just saw, and it does it atomically. So either it goes through all of it or none of it. You can't get interrupted in between. Lastly, and this is really important, this is like quiz question stuff, that when you receive a signal, it does not mean that you're going to run immediately. All it means is that your state is going to change from waiting to ready. It does not guarantee execution. It just guarantees a change in your state. And that's very, very important, as we will see. Okay, so these are the properties of condition variables. Now let's look at the design pattern. I got questions. I'll look at it. It seems like I have answered the question already, but I'll go through them. So how do we use condition variables? So this is like a design pattern. So the method or the thread that wants to consume, sorry, it wants to wait, as always, lock the mutex, unlock the mutex at the beginning and end. So these two should now be pretty familiar to everybody. At the beginning of our function, at the end of the function, we call lock and unlock. Now, in the middle, we're going to do a bunch of stuff. Then comes the condition that we want to check and potentially wait on. For example, if we are the producer, the condition that we want to check is if the queue is empty or not, right? Now, because we have locked the mutex, we have exclusive access to the queue, so we can check the state of the queue and see if the queue is empty or if it is full or what state it has. Now, let's say we check the state and we realize that the queue is full, and now we want to wait. So we check the state, the shared state that we want to check, and if it is not how we want it to be, then we want to wait. So here we call the condition variable .wait, and we pass our mutex to this wait function. Now, 2 points here. Internally, this wait, as I explained, is going to release the mutex and go to sleep. And this is going to happen atomically. Later on, somebody is going to signal us, and we're going to wake up. Now, when we wake up, we're going to attempt to internally inside wait. As you can see, we're not going to do it in our code. The system library is going to do that on our behalf. So the wait function on our behalf is going to attempt to lock the mutex again. If it is successful, that's good. It returns from wait, and we have the mutex. If it is not successful, then it could get blocked again inside wait. But eventually, we don't care. We're going to get out of wait with the mutex locked. Now, as you can see here, I have this while here. I'm going to check it in a while loop. I'm not going to check it in if loop. I'm going to check it in while loop. The reason for this is, as we will see, I have a slides to go over this example. What happens if instead of while we have if, is that when we got a signal, it basically indicates that what we were waiting has happened, right? So good. Now, the only difficulty is we're not going to run immediately after we get the signal. If we run immediately after we get the signal, then the condition should be true, it still should be true, right? But because we're not going to run immediately, there is a possibility that some other thread comes in and the scheduler picks them over us. Now, if another thread comes in, now we are ready, that other thread is also ready, and a scheduler might pick that other thread over us. let's say we were a producer and the queue was full, so we went to waiting. Now a consumer thread came, consumed an item, and sent us a signal, and we woke up, but we still are not running. Now, let's say that consumer exits, and right before we want to run, another producer comes, and out of luck, the scheduler picks that other producer. Now that other producer comes in, they lock the mutex, and they consume that. They put an item in that empty slot that we got signal for, and then they exit, and now we are running again. So we wake up. What should we do? We should again check the state. If we don't check the state, we're not sure that the signal that we got is still valid in terms of the condition that we wanted to happen for us to wake up. Because as I just described, there's a possibility that somebody else comes and changes the state again, and we might actually have to wait for a second time. Now, let's look at the method that sends a signal. Again, as always, lock, unlock. Now you do your stuff. And then at some point you want to signal, you just call signal. If instead of signal, you call broadcast, so signal wakes up only one waiting thread. Broadcast wakes up all the waiting threads. So everybody who is waiting will wake up. So that's the difference between signal and broadcast. Now let's look at all of this in a context of a bounded buffer example. So we're going to define our monitor. So I'm defining a bounded buffer mutex, and I'm going to have two condition variables. One condition variable for empty slots, and one condition variable for full slots. Now, here is the producer, the code for the producer. Things to note: locking the mutex and unlocking the mutex at the beginning and end. Now, checking the conditions that we want to check in a while. So again, very important, I'm using while. So as long as the buffer is full, I'm going to wait. And if I wake up, I have to check the buffer again until the buffer is not full and I can produce. Then I produce my item. And after I produce item, then I can send a signal if there are waiting consumers. So if a consumer is waiting, then I can send them a signal. Now let's look at the consumer code. It's gonna. I should. So sorry. This should be bb mutex dot lock. And this should be bb mutex dot unlock. So that's that. Now with the consumer code, I want to check the condition if the buffer is empty. And if it is not, I'm good to go to consume. But if it is empty, then I want to wait. And then I wait on this empty cv.wait. Once I consume an item, I can send a signal to the producer and tell them that there is an empty spot. So one of them can come and produce. Okay, I think this is a good place for me to pause and see what questions you guys have asked. So do condition variables buffer their signals such that if a consumer starts waiting after a signal is set, it will still receive the signal? Yes, yeah, we answered this question, no. So it's memoryless. We're not going to buffer signals. In semaphores, we do buffer V's because V is going to increment our variable. So it kind of gets buffered by definition. But in condition variables, if you send a signal and nobody is waiting, then your signal is lost. What's the difference between signal and broadcast? I answered that question. When a thread is in waiting and is woken up and is scheduled, will it still lock the mutex? Internally, yes, right? Inside the wait, when you wake up, you will wake up inside this wait function somewhere right after go to sleep. So you will wake up the line right after this. And the one thing you want to do, so this is, you have, your state has been changed from waiting to ready, and then eventually a scheduler picked you, so your state changed from ready to running, and now you're running eventually. What do? You just do m.lock. Now, if you're lucky and this mutex is not locked, then you will be able to lock it and you get out of wait. If you're unlucky and the mutex is already locked by someone else, then you will be suspended again. So your state will change again from running to waiting. Now this wait is on this mutex. It's not on what you initially wanted to wait for. So initially, for example, you wanted to wait for the queue to be empty or the queue to have an item for you to consume. So that was the reason for you to wait. And that's why you called wait. Now this second time, you're going to be suspended because the mutex is already locked by someone else. So therefore, you have to wait again for the mutex to be released or unlocked so that then you can lock it and continue. Okay, so yeah, so we talked about this. So when a producer calls empty cv.signal, it's going to go and wake up a consumer if there's any. And when the consumer calls full cv.signal, it's going to go and wake up a producer if there are any. Now, the question, so the point I was making is, this while, and the fact that it has to be a while, not an if. And I mentioned that if it was the case that when we get a signal, we start running right away, then you don't need this while, right? Now, that implementation where after calling signal, the waiting thread runs immediately is called Hoare implementation. And so these are the two implementation, Hoare and Mesa. Now, in Hoare implementation, this is what's going to happen. So let's say you lock the mutex, you check the queue and note that it's if, because it's a Hoare implementation, and you called then wait, and you got suspended. So you got suspended, and then another thread started running. They locked the mutex, and then they called signal. After the signal, what will happen in Hoare implementation is we're going to immediately come to you. So we're going to give you the mutex and give you the CPU. So you're going to run immediately after signal. So the running thread who called signal gets suspended here, and we context switch to you atomically. In this implementation, if this is the way that your monitor is implemented, then you don't need a while. You can just go with if. And once you're done, let's say here you unlock the mutex, then you give the mutex and CPU back to the thread that called signal. And then the signaler continues. In Mesa implementation, it's different. So what happens is the one who is going to send the signal, when they call signal, nothing is going to really happen other than the waiting thread is going to be changed. The state of the waiting thread is going to change to ready. That's all that is going to happen. We're not going to context switch to that guy. None of that. Like, we're just going to make it ready. We might context switch, but we don't know. There's no guarantee that we will context switch to that thread. What is guaranteed, though, is that the state of that waiting thread is going to change from waiting to ready. That is guaranteed. Now, if we indeed, the scheduler decides to context switch now, it's fine. We can context switch, but you will see that it's not a good idea to context switch, right? The reason is, if we context switch to, let's say we were here, and then we change the state to ready, and let's say the scheduler decides at this point to go and run the other thread, what happens is the other thread is going to wake up in the wait and try to unlock the mutex. Now, unfortunately, the mutex is locked by the signaler because signaler hasn't had a chance to unlock it yet. So then this guy is going to sleep again. So what's the point, right? So, but anyhow, this is guaranteed that your state will change to ready, but the rest is not guaranteed. Now you finish, and then once you're done, at some point in the future, the scheduler will pick the other thread to run. And this is the difference between Mesa and Hoare monitors. Now, one thing to note is why do we need this while? So I kind of like glossed over this example that if instead of while you have if, then you're in trouble. Let's look at it concretely in this example. So I have just the code that we saw on consume and produce. The only difference is I made the if, I changed the while to if. Now let's assume that we're doing Mesa monitors, not Hoare monitors. So we're in Mesa, which means that only the state is going to change, and we're not going to context switch immediately. Now see if we use if, what happens? Okay, here's an example. Let's look at that consumer producer example. So this is the queue. This is the bounded queue that we have. This is the state of our monitor. So our monitor has a mutex, has empty CV. It also has a full CV. But because I'm not using the full CV, I have dropped it. It exists, but in this example, we're not going to use it. So I don't have it here. So this is okay. This is our queue. This is our monitor. This one is the CPU state. So basically, which thread we're running, what is the ready queue at this point. So initially, right, let's say we're initially running T1, and T1 is a consumer. Okay, what happens? So the consumer comes in, calls the mutex. So now the mutex is locked, as you can see. The mutex is locked. Now it checks the queue. The queue is empty, so it calls wait. Now what happens is we put T1 in the waiting list on empty CV. So if you look at empty CV, now T1 is there, it's waiting, right? And the mutex is unlocked. As I said, this is going to happen atomically. So we're going to unlock the mutex, and we're going to put T1 in waiting, and it's going to be in the empty CV queue. Now let's say at this point, let's say T2 comes, and let's assume that T2 is a producer. So producer comes, it locks the mutex. So mutex is locked by T2. It checks the queue. It's not full, so it has empty slots. So the producer produces an item, so adds its item. Now the item is sitting in the queue. Next thing the producer does is it calls signal. Now what does this signal do? It removes T1 from this empty queue and puts T1 in the ready queue. it says now your state has become ready. And eventually, it probably terminates. But let's say that in the meantime, T3 comes in. Now, when T3 comes, let's say T2 is still running. So T3 also goes to ready queue. It's a new thread. It's a new consumer. And it goes to the ready queue. Now, let's have an overview of our system. So the producer has produced one item. The mutex is locked by T2. Nobody is waiting on this empty CV. T2 is running, and T1 and T3 are waiting. Not waiting. They're ready in the ready queue. So they're ready to execute. Now let's say that T2 terminates. So we're done with T2, and now the scheduler wants to pick the next thread. Let's assume that T3 is the lucky one and gets to run. So next, we start running T3. So instead of picking T1, which was signaled, we picked T3. Now what's going to T3 do? T3 is going to call the mutex. So mutex now is locked by T3. It will check the queue, and queue is not empty. There is one item here. So it doesn't wait. It just consumes it. It removes that item, and it exits. Now T3 has terminated. Now it's turn to go to T1 because T1 is ready. So we start running T1. What do? Now we wake up here inside wait, and we get out of wait. What do? We call this item equals queue.remove. But as you can see, this is going to have error because the queue is actually empty. The item that we received the signal for was consumed by T3. And because I didn't have a while here and I only had an if, I didn't check it again. And as a result, I got an error. To just get rid of this error, I need to have a while here instead of if. So had I had a while, I would have gone to sleep again and nothing would have happened. Okay. So hopefully that's a good introduction to condition variables. Now let's talk a little bit about the implementations and what is available, what is not. Now, in terms of the Mesa versus Hoare condition variables, Hoare condition variables are usually only used in textbooks for teaching purposes. There are no actual implementation of Hoare condition variables. The reason is because they're very complex. The way they work, like you have to, the signaler has to be suspended, and then you have to pass the mutex and the CPU to the waiting thread, and implementing that, all of that, and all the difficulties that come if you have a multiprocessor and such, has led to Hoare-style implementation to be just there for theory, for people to talk about what if we had, Hoare-style condition variables. But there's no actual implementation that I know of. So there might be one. Somebody has maybe implemented it. I don't know. None of the mainstream languages and system language libraries have implemented Hoare-style condition variables. In pthreads, in Java, and in almost all the other mainstream libraries, the monitors are implemented using Mesa style, which only changes the state from waiting to ready. It doesn't context switch right away, or like not just context switching. It doesn't transfer the mutex and CPU at the atomically to the one who receives the signal. So that's first thing to note. So usually if you're using any mainstream library, rest assured that you're using the Mesa style condition variable. So that one thing to note. Now, the second thing to note is you may wake up inside wait without even getting a signal. And this is a bug, but this bug actually exists even in Java. So if you look at Java user manual, you can see that they say that you might actually wake up for no reason. Like even without receiving a signal, you might wake up for some reason. We don't know why. It shouldn't happen, but they're saying that this could happen. So this actually tells you that you definitely need to have this while, because you might wake up for no reason. So check the condition again. And if the condition doesn't hold, go back to sleep. So put yourself back to sleep. So anyhow, don't forget about this while. Never use if with condition variables. So I guess we talked about this one. This is slide. So we can just jump over the first few ones. Now, if you remember when I started talking about semaphores, I said that semaphores are used mainly as the synchronization object in Unix. And sometimes, although, okay, let me take a step back. So when it comes to your applications that you're going to design going forward in your career, as long as you can, use condition variables and mutexes over semaphores. Try to avoid semaphores as much as you can, because semaphores are going to make your code ugly, hard to debug, hard to analyze, hard to understand and read. So try to avoid as much as possible. There will be times where you will need to use semaphores. One example is if you want to implement synchronization in your interrupt handler. Now, let's say, here's an example. Let's say that you have this shared memory that is going to be used by the device and the kernel. So there is this memory that the device driver and the kernel is going to use. Now, obviously, your device has no idea about semaphores or anything in any software lock, right? Now, if you have this kind of like shared memory and you want to protect it, you might think of your kernel threads might want to see, for example, if this data is not ready, they want to wait, right? So this is possible to want to wait if this particular memory that is shared between the kernel and the device is not ready to be used. So that's fine. Now, this wait needs to be signaled. Now, if the interrupt handler needs to, signal the kernel thread that was waiting, right? So let's say your kernel thread, like you have a daemon, I don't know, like I'm just making it up. Let's say your SSH daemon is going to wait for packets to come. So it's going to call wait. Now, let's say you get a packet and your NIC will put the packet in memory and then it raises an interrupt. Now, interrupt handler is going to wake up and it sort of wants to tell the SSH daemon to wake up and use the data that has arrived, right? Again, this is a made-up example. Now, can your interrupt handler use mutexes? Is it a viable option for your interrupt handler to use mutex? Now, if I go back, I want to remind you that I told you to, when you're using semaphore, oh my God, had I known that it's this much back, I wouldn't have done it. So this is the point I made. I was like, if you're gonna use wait, signal, or broadcast, make sure that you are holding the lock. Make sure that you have locked the mutex. Now the question here is, can I make the interrupt handler call mutex.lock? And the answer to that is absolutely not. Why? Because interrupt handler is not a thread. You cannot suspend an interrupt handler. If you make your interrupt handler to use a mutex, if it's going to say mutex.lock, so any code that calls mutex.lock is going to get suspended if that mutex is locked. And interrupt handler is not a thread. It's not schedulable. We're not going to schedule interrupt handler. Interrupt is going to happen, and the hardware is going to start running the interrupt handler code. So it's a terrible idea to use mutex for your interrupt handler because it's not schedulable. And if you use it, if you accidentally do such a thing, you might end up in deadlock. Why? Because let's say your kernel thread has the lock, the mutex, on some other thread, and then the interrupt handler also wants the mutex, calls the lock, and now you have a deadlock, right? Because the thread that was interrupted, that holds the lock, that has locked the mutex, wants the interrupt handler to finish so that it can run, and the interrupt handler wants the thread that has locked the mutex to finish. So now we have this dependency and you have a deadlock. So it's not a good idea, and we're not going to use that. So what can we do? This is one exception to what I said before, to always lock the mutex. You can, if you want, just use the signal without locking a mutex. Just call signal. And this is called naked notification, because you're just notifying without locking the mutex. And again, the reason that you're doing it is because you don't want to lock a mutex inside your interrupt handler. Now, this is kind of like not pretty, right? That you're using condition variables and you're not using proper way of using them. So one way to avoid all of this is, instead of using wait and signal, is to use P and V. So use the semaphore, and that is fine. So your interrupt handler can use V to signal, and your kernel thread could call P. So this is one example where semaphores might be preferred to condition variables because of the difficulty with mutexes. But generally speaking, this probably will never happen to you, probably, if you're not going to implement any operating system in the future. Maybe you do. Maybe you get to, be a operating system designer. I don't know. I'm going to sit. I'm tired. So I don't know. That might happen. But if you're not going to do an operating system implementation and you're going to just use parallel programming for your day-to-day job or something like that, then you probably will be happy with mutexes and condition variables without any problem. Okay. Okay, so what time is it? Okay. Lastly, let's talk about if, you know, I just spent so much time talking about mutexes and semaphores and condition variables. You might think, can I just avoid using these guys? Is there any way to avoid using this? And the answer is yes. So there is a programming style called communicating sequential processes. This is called CSP, and you can find it in Google Go. And this is a style of programming, and in this style, you don't share data. So there is no shared data. There are no two threads that access the same data. And if that happens, then you don't need synchronization. So we need synchronization only if we have data race. If there is no data race, then you don't need synchronization. Now, let's try to see an example how this could happen. So I'm going to just turn this bounded buffer that we've seen so far multiple times. We saw the implementation of it with mutexes, with semaphores, with monitors. And now let's look at an implementation where it's race-free, it's data race-free. So the way this works is, let me actually go up. So oh, what does that mean? Center divs. So somebody says I'm going to center, is that center devices as my day job? Elaborate. What does center divs mean? I'm familiar with that terminology. Okay. So in this implementation, instead of having shared data, we have message passing. So each thread is having access to its own data. And if that happens, then no thread is sharing data. Now, if one thread wants data that is owned by another thread, it just sends it a message and tells that thread to give me the data, right? So this is kind of, if you're familiar with Go, it's kind of like those channels. So you have these channels and you have message passing. So data is going to be passed through these channels, and everybody is in charge of its own data. And if you want data that is owned by someone else, you just send them a message. You say, give me the data. And if you follow this way of implementing, then there is no data race, right? Although this is a little bit tricky because eventually you cannot avoid it, actually. So if you, like, for example, in Go, implementation of these channels requires synchronization because the channel becomes that shared object. But anyhow, from the perspective of the programmer, though, they don't need to deal with locks and semaphores. So the system library takes care of it, right? So again, I'm talking about the high-level programmers. If you're using Go and using these channels, you don't really care about, you don't use locks and mutexes and condition variables and semaphores. You just send messages, and the library under the hood is implementing those channels in a synchronized way. So let's look at an example. So here if you have a bounded buffer, so if this is your buffer, you put a single thread, let's say T1, is in charge of this guy. Now, if anybody wants to put an item in the buffer, they send a put message to T1. If they want to get an item, they send a get request to T1. So this is the code for T1, for example. So T1 keeps getting messages. So it has this while loop that receives messages. If the message is a get, then it looks at the queue and does stuff, right? If the message is a put, it looks at the queue and it does what it has to do. Now, because there is only one thread accessing this buffer, I don't need to lock mutexes here and here or here and here, right? Because I'm the only thread that accesses the buffer. So there's no data race. So that's another implementation. If you want, this option is available. I personally am in favor of this. So this is a lot cleaner to understand and implement and all, right? And it's kind of like similar to actor model. For those of you who are interested, you can actually look at actor model, which is basically the idea of having actors and they have inboxes and so on and so forth. Okay, so just a point to be made in terms of performance. There is no actual difference between the CSP, which is the one that we just talked, and monitors, for example. So in monitors, you use mutual exclusion for shared data. In CSP, you assign a single thread to do the operations. In monitors, you call methods on the shared data. In CSP, you send messages. In monitors, you have a wait condition. And so in CSP, you have these conditions. For example, I kind of like glossed over it, is here, right? If, for example, the queue is empty, then you sort of have to wait, right? So I can't answer your signal, your message right away. I have to wait until somebody puts an item, then I can respond to your message. Maybe I just return an empty, like there's nothing in the queue, so you can't get anything, and then you have to retry, or I just wait for your response until somebody puts an item, but there is no way to get rid of this waiting. So in monitors, you wait on condition variables. In this one, you just wait inside your functions. The same with the signals. So they're very similar. They're just two sides of the same coin. It's just which one you're more comfortable using in your code and which one gives your code a better, better reliability, better debugging experience, better reading and understanding experience. And again, personally, I'm in favor of CSP, and seems like most programmers are in favor of this. But it's a matter of preferences. You might actually like using mutexes and monitors and semaphores better, but they're very equal. Okay, so the last topic I want to cover, and I have like about 15 minutes, is deadlocks. So see if we can just cover this deadlock. So there is the issue of a starvation, which means that threads are going to wait indefinitely. So let's say you have a system and you have high priority tasks and low priority tasks, and your scheduler is going to just always pick high priority tasks. In that case, the low priority task is going to get starved. So this is called the starvation. You're going to wait indefinitely in the system, or there's a possibility for you to wait indefinitely. Now, that is different from deadlock. Deadlock refers to a condition where you have a circular weighting. So thread A owns a resource. Now, what is a resource? This resource could be a lock or a mutex, sorry. This resource could be a file, right? So thread I has exclusive access to this file. Now, thread A later on might need another file. For example, if in a context of a database, so thread 1 might need exclusive access to table 1, and then later on it wants exclusive access to table 2. Now, if table 2 is locked by thread B, and thread B needs table 1, now we have a deadlock. So this resource could be anything, any shared. It could be shared memory. It could be a database. It could be a file. You name it. Any resource that you can provide exclusive and mutual exclusion on, then you might have to deal with deadlock. So if I were to visualize this, excuse me, I have thread A and thread B here. Now, thread A has, let's say, locked the mutex, or locked this table, or has locked this file. So this file is now owned by thread A, and thread A wants resource 2. Now, we will have a deadlock if thread B owns this resource, meaning that it has locked it and has exclusive access to it. And now thread B wants resource 1, which is owned by thread A. So this circular weighting is called deadlock. Now, deadlock leads to a starvation, because if you have a deadlock in your system, thread A and thread B will never run, and they both get starved, but not vice versa. So if you have a starvation, that doesn't mean that you have deadlock. For example, in the case of high priority and low priority tasks, there's no deadlock, right? The high priority tasks are just executing, but the low priority tasks are starving. Now, there is this very famous dining philosophers. I'm not going to use philosophers because philosophers are intelligent, and this dining philosophers example assumes that they're dumb, but they're not. I mean, compared to engineers, they might be, or scientists. I hope I don't get canceled for this, but anyhow, so never mind. Let's talk about politicians, because those actually are often than you want them to be dumb. I hope I don't get into trouble for that. But anyhow, I'm teaching operating systems, so let's call this dining politicians, for the lack of a better term. Now, there are 5 of them, let's say, around the table, and for some peculiar reason, we have 5 forks as well. So 5 dining politicians and 5 forks. Let's say that everybody is right-handed, so they're going to just pick the right fork first. And let's say everybody needs 2 forks to eat, weirdly. Now, if everybody picks the fork on their right, then all the forks are gone. And now everybody attempts to pick the fork on their left, and there are no forks. And here we have a deadlock, and all of the politicians are going to just sit there until they die for the better society. No, so yeah, anyhow. So this is deadlock, and this is an example of dining politicians. I'm not a big fan of them. Now, so this one, I have a chopstick instead of fork, but let's go with fork. So I kind of explain all of that. Now, here is another example. This is a wormhole routed network. So let's say there is this turn for trains. Train 1 comes and wants to turn right. Before that happens, train 2 comes, and this one also wants to turn right. But before it turns right, train 3 comes and it wants to turn right. And then train 4 comes and it wants to turn right. And now you have a deadlock, obviously, because everybody wants to turn right, but the resource that they need is owned by another train. It's occupied by another train. Which party to the politicians? Oh, which party the politicians belong to? Does it really matter? Is there any difference between these parties? You tell me. I mean, I don't see any difference. Don't make me talk. Okay, so this is another example. Let's move on. There's not much to talk about. So this is just an example. Now, what are the conditions necessary for a system to get into deadlock? So there are conditions that have to be met for us to say now we have deadlock. If any of these conditions don't hold, then we don't have a deadlock. And even if all the conditions hold, you might still not have a deadlock. So we'll talk about that. So these are necessary conditions, but it's not, what is it? What do they call necessary and something? But anyhow, so these are necessary. So if any of them do not hold, then you don't have a deadlock. But if all of them hold, you still might not have a deadlock. The first one is, oh, okay. So, right. So this basically explains what I just said, that you might or might not get deadlock, even if the conditions hold, right? This is an example. So this is very similar to the example we just saw at the beginning of this lecture, where we called P and then we changed the order of P and we saw that it led to deadlock. So this is an example, right? So we have thread A and thread B. Thread A is going to call first P on X and then P on Y. And thread B is going to call P on Y first and then call P on X. And there is a possibility that this leads to deadlock. For example, if A comes first, so we have X and we have Y and we have A and we have B. So let's say A comes and calls X. So X now is owned by A. Let's say at this point we context switch to B and B calls Y. So now Y is owned by B. Now, if we continue with B and B calls P, now B wants X, but X is held by A. So we're going to context switch to A, and A is going to call Y, Y.P, and now we have a deadlock. So this interleaving between A and B led to deadlock. Now, there might be another interleaving that doesn't cause deadlock. For example, here is X, here is Y, here is A, here is B. Let's say A calls P on X, so it owns X, and then it calls P on Y before we context switch. So now these two hold. So A now holds both of them. Now, if we context switch to B and B calls P on Y, it's going to get blocked, but we don't have a deadlock, right? So deadlocks are not always deterministic. So they might happen or they might not happen. So you might, write a piece of code, you test it 100 times, 1,000 times, and it all works, and then you deploy it and it gets deadlocked. So so that's that. Now let's talk about requirements. So it was required but not necessary. So these are required but not necessary. Okay, so The first one, you need mutual exclusion, meaning that you have to have these resources that are owned by a single thread. So if resources have infinite, access to them, then you might not have deadlock. So mutual, meaning that, so the first one says that resources should be owned by a single thread. The second one says you have to have this wait and hold condition, meaning that a thread that calls, mutex.p and y.p goes to waiting while it still holds x.p. So x has been owned by A, and now A goes to waiting. So you go to waiting while holding the resource. So this is hold and wait. So this is the second condition necessary. Third condition is no preemption. So it means that you're not going to be preempted, meaning that we're not going to take away the resource that you have, right? Unless you voluntarily release that resource, nobody can come and take that resource away from you. Like the mutex, right? If you call mutex.lock, we can't force you to unlock it unless you call mutex.unlock. So we have this no preemption, meaning that I cannot take away the resource that you have. And fourth condition is this circular waiting, meaning that if you have a number of threads, you need T1 to need a resource to hold the resource while waiting for a resource that T2 holds, and then T2 has to hold the resource that T1 wants, but then it has to want a resource that T3 holds, and so on and so forth. So you have this cycle of somebody owning and wanting something else, which is owned by somebody else who is waiting for something. So you could get this condition where you have X, Y, and Z, and X is owned by A wants Y is owned by B wants Z is owned by C, and C wants X. And this is the waiting cycle. So everybody holds a resource but wants a resource that is owned by someone else. So if you have all four conditions, then you could have a deadlock. But if any of these conditions don't hold, then you don't have a deadlock. So I got a question. It's like the game Rush Hour. Where you have to get a bunch of parked cars out of the board. Yeah, sort of. Okay. I guess I'm gonna stop here because we're out of time. Let me just see. Discord. Okay. Okay, I'm almost done. Almost. So we're at slide 83, and we probably okay. So I was hoping that I finished the synchronization, but unfortunately it didn't happen. But it's fine. So on Thursday we'll finish hopefully this and start talking about implementation of threads. Hopefully we're going back to talking about operating systems. Now again, I'm reiterating what I said at the beginning of the lecture. So tomorrow we will have a tutorial session, and I will talk about another example other than this bounded buffer, and we'll try to implement it using monitors. So this will be a good practice to use mutexes and monitors, and then we answer a bunch of questions. Now after that, during your quizzes, you will see I think in 3 or 4 quizzes, we'll just see more examples of condition variables. It's going to be a recurring question that you will see in your quiz, but different implementations, and you will be asked to see what properties each implementation has. So if like you want to prepare for the exam, sort of have a good idea, definitely try to attend the tutorial tomorrow, or if you miss it, just watch the recording of it. Okay, well, that's it from me. I hope you have a great afternoon and evening, and talk to you on Thursday. Take care, be safe. Bye-bye.